we've done this house party, and on a certain level it's kind of fun to watch and think about. But you have to appreciate that on a molecular level, what I've just shown you is the way it really happens. You have these systems, and they are filled with molecules that undergo chemical or physical processes. For reasons that are not all that important to this course at this point, it is the case that there is going to be a certain value thermodynamically associated with whether the reaction happens or not. I never tell you you have to tell me what delta G is. I never tell you you have to tell me what K is. But I do tell you this, that if I tell it to you, you need to be able to tell me how the system responds to it. So if I tell you I've got K equal to 1/2, that means you've got to look at your system and organize it so that the stuff on the right over the stuff on the left equals 1/2. If I suddenly tell you that K is equal to 1/72, then you've got to organize things so that you've got the stuff on the right over the stuff on the left equal to 1/72. It's also important to appreciate that these K values are temperature dependent. And that's good and bad in a variety of ways, but the nice thing about it is it means that if I go look up data in a book, I will find the K value, and that K value is going to be correct for that chemical reaction. For boy plus girl makes boy-girl, or for 3 hydrogens and a nitrogen making an ammonia, or 2 hydrogens and an oxygen making a water, there is going to be a K value for that, just like there's a delta G value for that particular temperature. And you can always find those values. You can pull them out of the tables as K values in the same way that you can pull out thermodynamic data. And something else that's kind of nice is that in a little bit I'm going to show you how you can take the temperature dependence that's associated with that and develop an equation just like the Clausius-Clapeyron equation. But now, instead of it being a temperature-dependent Clausius-Clapeyron that tells you about vapor pressure, I'm about to show you a new equation called the Van't Hoff equation. This Van't Hoff equation that we'll see in the next lecture allows me to calculate what K would be at different temperatures. It would say, if you tell me K is 1/2 at room temperature, and then you tell me that K is now 4, I'm going to tell you how cold it got. Or if you tell me that K is 1/2 at room temperature, and you told me that it got up to 87 degrees outside and was really hot and sunny, I'd be able to tell you that K was 1/72. So even though I show you this house party and it's all done with people and people running around in rooms and all this sort of thing, do understand that at root, these core ideas about equilibria and about stresses and the ability of these molecules to somehow miraculously always finding themselves, no matter what combination you have to start, in the right combinations to get the K value you're supposed to have, whether you're in Russia or whether you are in the US. Your temperature's right, then guess what? Your K value is going to be the same everywhere.